is in the paper, but they sort of didn't tell everybody that the 16-ton piece landed a quarter mile away. If it had landed on somebody's house, the news people might have picked it up. But I can tell you that the safety officials, the fire department, the police department, and the mayor's office, they were not happy to know that they had a plant that actually had something that could be sending 16-ton pieces a quarter mile away in a random direction. Okay. So anyway, but the really interesting thing to me about this was the world's only vessel that could do all the aircraft engines in the world. But fortunately, the company, there was a growth in the business, and they had another one coming on stream. They had ordered it about 3 years before. It was coming on stream in 3 months. So we didn't see a multi-billion-dollar problem.
Was the new one made right?
Yeah. Well, first of all, this was 10 years after that. And there have been some improvements in quality control in the mills and understanding of the heat treatment, the water treatment, and also calculation of stresses and things. But those types of things, the calculation of stresses, I'm sure that in some of the videos you're going to hear about the Navy's internally cooled recuperator on the surface ships, and how originally it was supposed to, this is just a big heat exchanger, take the stack gases from the oil-fired ships, and preheat the incoming air so you get more efficiency. I mean, when you're just kind of cruising along a nice lazy stroll through the Pacific or something, you're operating at about 10% efficiency because most of your heat's just going up the stack. You're not full out battle speed or something. And so it turns out the problem is you have to go back to the carrier to refuel. Is that right, for the destroyers and stuff or something? Yeah, okay. But that can be when you're back in the days of the former Soviet Union, when people could hit you with something that has a very wide range. Some of your other ships could be 30 miles away from the oiler or the carrier. Okay, and so they were spending half their time off station, just going back to get fuel. Okay, so they decided we can up our efficiency to 30% with this heat exchanger. They built this heat exchanger. And they found that it lasted for not 100,000 hours, but about 2 minutes, okay, before it tore itself apart, due to the transient thermal stresses, okay? Similar type of problem. They fixed it, and I'm told now you actually do have ICRs in your ships, but, pardon me?
The British did.
Oh, okay. Well, maybe we still don't have them, but who knows what's going to happen. But I remember I ended up being on a, what they call a blue ribbon panel, and we had to go out and look at it and say what was wrong and all this other stuff. Now, for hipping, you can get dramatic improvements in properties such as fatigue properties. This is actually applied stress versus cycles to failure. So this is just a fatigue curve, and you actually go up by about 20% in stress. But 20% in stress in terms of fatigue life is like a factor of 400% in life, okay, because of the slope of that curve. You know, this way it's 20%. In that direction, in high cycle fatigue, you get some very large increases in life, okay? So that's why you can afford to spend $1,000 an hour to put some of these things through there. And when you put them in the vessel, you're not just putting one disc or one cylinder or whatever in there. You're putting half a dozen discs at a time, so you spread it out a little bit that way. Okay, so hipping is one way to make a net shaped part. Now let's finish up a little bit on solidification. If you, how many of you have, I may have asked this before, how many of you have not seen a phase diagram before? I think most of you have seen a phase diagram. Okay, so a phase diagram is just temperature versus composition for an alloy. The pure material melts at some temperature. Many materials, you add carbon to iron, you add copper to aluminum, and the temperature decreases, the melting temperature decreases. You add salt to ice, and the temperature decreases and it melts. And that's the principle of putting salt on the roads in the winter to melt the ice. It's the principle of freezing ice cream. How does that freeze ice cream? Melting the ice. Have you ever thought about it? Haven't you ever frozen ice cream? Made homemade ice cream? Yeah, you have to, in order to melt the ice, you have to absorb the latent heat of fusion. Okay? Well, if the ice turning to water is absorbing heat, it's got to get that heat from somewhere. It gets it from the cream that's in the ice cream, and it freezes the ice cream. It's sucking the heat out of the ice cream. Okay? So anyway, that's just, you know, you got to think of your thermodynamics when you're...
That sounds like a homework problem.
Homework? Yes, it would be a good homework problem. Okay, go make some ice cream, right? In any case, this is, you have a liquidus line, you have a solidus line, and the solidification folks like to describe that in terms of a partition coefficient, K, and K is just the composition of the liquid over the solid. Okay, so this composition over that, and so the first solid to form will be KC0. The average composition is whatever your average composition of your melt is, and the solid that forms will be K times C0. And what happens is, if you first form a little bit of liquid, as you form more and more liquid, you've solidified along here, the liquid is getting enriched in the B phase, or no, the B component, and so it starts to increase in concentration of the alloy, and the liquid composition, they're assuming perfect diffusion in the liquid here, which is not really true, but in any case, you will actually sweep the concentration of the B component to the end of this thing if you solidify in one direction. And this is the principle of zone melting. Anyone ever heard of zone melting? Gee, it was a big deal when I was a student, because that was what happened in the 1950s when they first invented semiconductors at Bell Labs. You needed very, very pure silicon or germanium. And by very, very pure, we mean like 6 or 7 nines pure. And now 6 nines pure, what do we mean by that? Anybody know? 99.9999. Yep, 6 nines. Exactly, okay? 1 part per million in purity. And 7 nines is 1/10 of a part per million, 100 parts per billion in purity. And that's what you need in silicon or germanium to make good semiconductors. Well, how could you make that? Because the things will actually, they'll start to react with the wall of the crucible. Okay, give you that type of impurity level. And so it turns out that there was a technician at Bell Labs named Fan. I think he had a high school diploma, but he certainly didn't have a college degree. And he was the one who said, well, let's just keep melting it in one direction and sweep all the impurities to one end of the ingot. And so he put silicon in a little boat, and he just pulled the boat through a furnace. As it cooled, as it solidified, as he was pulling it through, he was sweeping all the impurities to one side. You do that about 10 times, and you've got something 6 nines pure. You just take all the impurities and just keep sweeping them to the other end, cut off that end of the ingot, and you've got the crystal. That's still how we make really good quality silicon today. For all the whole semiconductor industry is based on simple partition coefficient and solidifying things in one direction. Now you have to do it like 10 times to keep sweeping all your trash to the other end, then cut off the end, okay? So all of a sudden in the 1960s and stuff, remember I was a student in the 60s, you could buy 6 nines pure tin or aluminum. I mean, it's no big deal today, but back in 1950, that would have been a big deal to have 6 nines purity metals. Because if you want to go through the thermodynamics, entropy says that's a very expensive thing to do to get the last few impurities out, right? You know what I mean by the entropy thing?
Delta S.
Yeah, delta S. Basically, as you get to 100% purity, entropy goes to infinity, okay? To get that last little bit of stuff out of there, okay? It's delta S, ds dx, if x is your concentration. Hey, you're learning some math. where XB, as XB goes to 0, goes to infinity, okay? It takes infinite entropy to get the last atom out of, impurity atom out of there, okay? You can prove it through statistical mechanics. Anyway, so the point is, when you solidify something from one direction, you will get this segregation of your alloying elements. You'll get enriched in the liquid, and that leads to microsegregation, which you don't always want, which leads you to do a number of things. Now, if you don't assume, and I actually was going to spend some time on this, back when I was a student, they used to spend several lectures on what they called constitutional supercooling. I'm going to spend several minutes on it. This is that phase diagram turned on its side. Just flip it over 90 degrees. Temperature versus composition now, okay? So here's the melting point. Here's the solidus line. Here's the liquidus line. If you map that turned at 90 degrees onto this concentration, you find here's your C0, your average concentration. Here's your KC0, first solid to solidify. As you go along here, you're pushing the solute ahead in the liquid, and you actually have a boundary layer here, and you can start analyzing that. And what you find is, depending on how steep your temperature gradient is along here, because you're solidifying, this is colder than this. Okay, you're solidifying, you're pulling this boat through the furnace or whatever. You can get to the point where this K value is such that the material here is actually supercooled. This enriched B material is what we call constitutional supercooling. By throwing the extra B atoms into the front here, then you'll actually enrich it, and that stuff wants to solidify if there's a nucleus. Well, that's exactly what causes these dendrites, or these cells that we've talked about, in case you wonder why we have cellular growth, oops, or dendritic growth. Okay. Here's cellular growth. You actually have, if you have a very steep gradient of temperature, you can suppress this instability. Here's a little instability. Here's a big fully cellular growth. When it gets really unstable, you get the dendritic growth, and basically you get instabilities along the side, and that creates the dendrites. And those dendrites create porosity in your casting, okay, because the liquid can't get past all those little branches. It's kind of like in a snowfall, you know. Underneath the fir tree, you don't have any snow on the ground because all the snow got caught up in the leaves, or in the boughs. And so it doesn't reach the ground. So this dendrites can be a big problem because they represent microsegregation, inhomogeneities, increase in porosity, regions within the casting that are rich in alloying element or deficient in alloying element, and that creates lots of problems. Now, why can that be a problem? The whole Seawolf problem, $2 billion it cost the Navy, was because the welding wire was too rich. It had too much of certain alloying elements. And it probably came from an enriched area of the casting. It was all drawn into wire, but they didn't draw the whole 20-ton ingot into wire all at once. They cut it up in pieces. And so this part of the ingot was rich. This part of the ingot was poor in alloying element. And the one they started using, the lot they used, turned out to be what they called high side chemistry. And if you had gone to that same ingot they made the wire from, you would find low side chemistry. Well, the problem with the high side chemistry, it had a yield strength of about 140 KSI, not 100 KSI, because it was enriched in alloy. And if you're at 140 KSI, your sensitivity to hydrogen is much worse. Okay, you can't tolerate anywhere near as much hydrogen. It was all within the Navy spec range, but it happened to be all the way at one end of the high side chemistry. Okay, they always give you a range because there are these inhomogeneities in the casting, right? And so they kind of got bit by segregation all the way back in the original ingot. Okay, so I'm just trying to point out to you that some of these things actually are important, and they do follow through the whole system and can sometimes create real problems for you. But we're not going to go through all the different ways that dendrites form. There are lots of nice little pictures of dendrites. Okay, here's where you've etched, well, doesn't show it very well. This one shows up a little better. This actually is dendritic structure in a transparent organic. So this is a organic liquid that's solidifying, and you get, these are instabilities along the side, and so we actually call this distance from here to here is the primary dendrite arm spacing, and the secondary dendrite arm spacing is the little distance in between. And it turns out that the size of the dendrite arms, or the spacing, is proportional to the cooling rate of the casting. So this is a plot from Fleming's book of local solidification time, which is one over the cooling rate. Okay, so this is secondary dendrite arm spacing over 8 orders of magnitude. Okay, we don't always plot a lot of real data over 8 orders of magnitude, but there's a correlation, and the secondary dendrite arm spacing, as I remember, goes to about the 1/3 power. The slope of this is about 1/3 of the cooling time, the local solidification time. If you cool really, really fast, let's say if you cool really, really fast, you're down here, and your secondary dendrite arm spacing is less than 10 microns, okay? That's rapid solidification, very little inhomogeneity if you cool quickly. If you cool very slowly, like a great big ingot, a 20-ton ingot, or a 20-inch thick piece of steel or something, you can have dendrite arms that are on the order of millimeters in size. I mean, huge dendrites. And you can never diffuse away in the solid state that inhomogeneity. It would take millions of years at temperature. So we have to do lots of things to try to get fast solidification. It turns out, if you look at the primary dendrite arm spacing, this plot's versus cooling rate, so it's got minus 1/3 slope rather than a plus 1/3, but it's just one case you're plotting cooling rate, the other one you're doing local solidification time. And this is a bunch of aluminum alloys, and it shows 100 microns to 10 microns. This type of stuff, months to diffuse away the segregation. This type of stuff, hours. So you actually could get a homogeneous melt if you do something like that. So, yeah.
Would you ever use a hip, for instance, to rid like any dendrites that are in the material?
No, HIP will not do it. Unless you start with something that's rapidly solidified powder, which has very small dendrites as a powder, and then you put the powder inside a jacket in the hip. So you make a metal can, maybe you got a nickel-based alloy, and you put it inside a steel can, which is sort of like just a big steel balloon at these temperatures, and you actually squeeze the powder together. So HIP is used for a lot of powder processing. We get rid of the segregation by doing rapid solidification of powders, but the powders, we have to weld them together. You weld them together in a HIP unit. Okay? So the point is, you like to have rapid solidification to get rid of this microsegregation, which creates variations in properties throughout your bulk. But if you just solidify it as a great big bulk casting, you're never going to get very uniform properties. Okay? The size of the imperfections are proportional to the size of the casting. If you make a micro casting, of a little powder, that size of a piece of cracked pepper, right? You can get rid of it in a HIP unit. Okay? Or you can do it other ways. You can center it together, and then you can forge it to help get rid of that porosity. But forging it means you have to, it's kind of like kneading dough. You've got to get a lot of strain into the material, which is actually where I want to go next, to talk about how we have to get rid of these structures. Now, there's one other thing that Fleming's actually invented a process in the late 60s. Well, I talked about the cellular growth and stuff. In order to inhibit the dendrites from forming, you can grow in a gradient furnace, and the steeper the gradient you have, this is hundreds of degrees C per centimeter or so, you can keep the dendrites from forming. And you sort of end up with zone melting, but if things aren't too bad, you're not sweeping everything ahead if you design it properly. But you have the gradient furnaces, and I didn't bring it with me again, but you see my little turbine blade, we passed it around. Those are grown in a gradient furnace. You can put, I think I told you, the Rolls-Royce uses 4 blades on a little investment casting sprue. General Electric and Pratt, their casting shops use about 16 or 24 on an investment casting sprue, and they grow it as a single crystal in a gradient furnace. It takes about 10 hours because you have about 1,000 degree temperature differential over 5 or 6 inches in this furnace. And you just slowly pull it through there over about 10 hours. And you don't get dendrites because you suppress it because of the steep gradient. You don't get constitutional supercooling that allows the instability for the cell to grow up into the liquid. Okay? You can get a nice plain front solidification, get a very perfect structure, but it costs a lot of money. This furnace, this gradient furnace, is about $3 million to grow, 16 blades a day, or maybe 32 blades a day or something. Okay, so you can start to see why these things start to cost, $6,000 a piece. But if they allow you to use half the fuel over the life of the engine, it's worth it, right? So it's just an economic analysis. So Fleming's actually showed that you could grow all kinds of structures off the equilibrium structure. This is a composite structure where you actually control the cellular growth, and you can, on a transverse section, you got the grass, you're looking at the top of the grass, this is one phase over another. Longitudinal section, you'll get stringers like this. The paper is called Growth of Composites from the Melt, and you're growing it in a gradient furnace just like these turbine blades. And so in the late 60s, everybody wanted to see if they could make better quality turbine blades and other things by using this gradient growth technique, and they do in various ways, but they found they needed to go not just to this structure but to a complete single crystal structure. So it was actually a very big deal when he did it, to show that you could get non-equilibrium structures by growing things in a very steep temperature gradient, and a lot of research was done on that. Okay, so any questions on any of that stuff? This is, did I show you this picture before of one of the generator rotors? Okay, does this have a person in it? I don't remember, this has got a person. Anyway, this is the generator rotor forging. And this is in one of the plants. I don't remember if this is U.S. Steel or Bethlehem Steel. Probably only one of them exists anymore in the United States. Bethlehem is now that steel plant is now an amusement park in Bethlehem, Pennsylvania. This is the stairs, okay, going up. So this is 1 floor, 2, 3, 4, 5, 6 stories, right, tall. And here's your forging. May run 200 tons. At this point, started out as about a 450-ton forging, and by the time you forged it and lost all the oxidation, because you had to leave it in the furnace for a week before you got it up to forging temperature, and you grew an oxide scale that's like an inch thick, and when you forge it, that all just comes off. So you have a lot of waste, and then you machine it, and you're going to heat treat it, and this was basically a system where they made battleship gun barrels in World War I. Okay. Not a lot of facilities like that in the world. A lot of crane capacity, a lot of big height and things like that. But, and that's generator rotor forgings. Now, if I want to get rid of the inhomogeneities, I could start with rapidly solidified powders, or I can start with castings. And if I give them 90% reduction, I can flatten out these dendrites until where I pancake them so that they're so thin that I can stick them in a furnace and diffuse out things. So who cares if they're a millimeter thick dendrite arm spacing? If I turn them into 1/10 of a millimeter, I can put them in a furnace and I can anneal it out, and I can do it multiple times, and that's basically what we do to get homogeneity in products by mechanical working. So we're getting out of solidification. Talked about the problems of solidification. How can you extract the heat? How can you get fine dendrite arms? How can you get rid of porosity? And things like that. So if I wanted to make a rotor disc for an engine, or even, well, it can be a jet engine, it can be a steam engine, okay? So these things could be more than 6 feet in diameter. They can be 10 feet in diameter if you're talking about a big rotor like we had before, the last rotor. You start out with a billet of material, an ingot that you cast, and you do a pancake forge. Well, that pancake forge, and people actually take plasticine, like Play-Doh, and they do some of the modeling of this. They used to do. Now you can do it in the computer. But before we had computers, we had Play-Doh. Okay, it's true. And you can actually squeeze down on it. If you squeeze too much at once, the friction is going to cause cracking on the outside. You get a barrel-shaped ingot as you start to compress it into a pancake. So you actually have to lift it off, maybe reheat it, come in again with a new frictional boundary condition, and squeeze it some more to get a big reduction in your pancake. The material will only take so much stretch before it breaks. And so, I mean, actually, look through look through things in my office, and here's a tensile specimen. If you pull on something enough, it will break. Okay, it will neck down and break. But typically, a metal will only give you like 30% stretch, maybe 60% if it's really hot, before it just breaks. And that's because you can model the metal as if it's a non-Newtonian fluid. Now, a Newtonian fluid is something that doesn't matter if it's different in cross-section. You can stretch it out and it will maintain the same general shape. If it had waves in it to begin with, you can stretch it out and it will keep the same general shape between the peaks and the valleys, okay, as a Newtonian fluid. Basically what we mean in a Newtonian fluid, we mean that if you look at the stress is equal to the strain raised to some strain rate. So this is d epsilon dt, okay? M is the coefficient exponent. A Newtonian fluid is when m dot equals 1. For a typical metal, m dot equals 0.2, okay? So if you have any instability in a metal where it starts to thin down a little bit, that instability will grow, it will neck down and break at the thin spot, or the small diameter instability. A Newtonian metal, you can have a little neck in there, and you can pull it out 100 miles if it really is an M of 1. Now, the only Newtonian fluid that we might work with typically is glass. Glass may have 0.9. Metals typically have 0.2. So when we want to forge something, we have to do multiple steps to forge it. To give you an example, if I wanted to make a simple little part, and this little simple part I'm going to pass around, is basically a little metal insert that goes into a piece of wood so that you can put a steel screw in it without stripping the wood threads, right? So you're going to insert this plug into wood. I mean, you put together cheap particle board furniture from Walmart and it has all these types of little inserts in it, right? To make that little insert, you start out with a little piece of wire that you chop off into a little, we'll call it our ingot, like that up there. This little chunk of metal, and you have to forge that. Now this is cold forge. The first one they size it, and it's got a little bit of a cone here, about a millimeter deep. Then they start to punch a hole in the bottom. They extrude a little hole, but they can't make it all the way because it would crack if they went any further. So then they do it again, they extrude it again. Then they put a head on it. Okay, then they have to, the one wasted piece of material, and is actually a little, they punch the hole out. Okay, and there's a little, I have the little hole there. It's underneath a little bit of tape. And then they do a finishing sizing. Then they knurl the threads on the outside. Then, or knurl the grip on the outside. Then they thread it on the inside, and then they plate it. So there are 11 steps of forging to make that part. Okay?
What do you mean by knurl?
Knurling is just putting that.
Do they inscribe it almost? Or?
Actually, they roll it on. They just have a hard tool that has the same shape, and they put it in a lathe, and they put the hard tool up against it and spin it, and it's called knurling it. Okay, just forms that. So I'll start it over here. Well, they make the same parts. They make parts that weigh 4 or 5 pounds that might go in the steering component of a truck or a car. Okay, if you look at the knuckles and the steering components of your, they are cold forged or warm forged. Actually, this is called cold heading, because in the old days, the first cold heading was just putting a head on a nail. Okay, and that's about all they could do before World War II. And then someone learned, if the rest of the course, when you get to adhesive bonding, I usually end up talking about how they learned to phosphate the steel so it would hold on to the lubricant. Okay, because a lot of the tearing and stuff was due to the frictional boundary conditions. As the steel is the steel of the part is rubbing against the tool that you're trying to forge it against, you can get welding between there, and if you keep on going, you're going to get surface cracking on your part. And you're also going to wear out your tooling very quickly. They learned to phosphate the steel after World War II, and the lubricant they use is basically soap. It's actually they call it a stearate, but it's soap. Okay, if you know what soap is, it's a stearate. Okay, and because they basically had this porous phosphate coating, it would hold the stearate, lots of stearate, and it would just smear that peanut butter lubricant all the way through, and they could not get terrible tool wear. They could head that through 11 dies rather than 25 dies or something. So it becomes cheap enough to make those parts. You go through a shop. You go through a shop with earmuffs. You don't just put little ear plugs in your ears when you go through one of these shops. Okay, this shop is probably 180 decibels when it's going, and it's just going. Bah, 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 bah. The forging machine. Typically, a little part like that, they may be going 7 times a second heading. Okay, I can't do it 7 times a second. Okay, but it's really pounding away, and they just spit them out. Okay, so let's take a break, and we'll talk about a little bit more about forging. Come back in about 10 minutes or so. You have to go through a lot of steps and a lot of different shapes before you get to the finished part. And to give you an idea of what you might have to go through, the Air Force likes to call this the buy to fly ratio. How many pounds of metal do you have to purchase to make a forging that you can then sell as a part? This is one where the finished part, this is part of one of these discs, weighs 11 pounds. If you do a cold die forging, it starts out at 210 pounds, so that's a buy to fly ratio of almost 20. And here's the hot die forging. If you do it hot, it's only 72 pounds, and so that's obviously better. And if you start realizing that we're talking about alloys here that may cost $100 a pound, okay? When you got a buy to fly ratio of 20, you're now paying $2,000 a pound for the metal that you actually fly, without even the processing that's involved, right? So there's lots of money to be made in what's called near net shape processing, okay? So let's see, I probably don't need to show you that. Here is an example of a billet, okay, which is just a big long bar. They roll the bar from an ingot, and so this could be 6 inches in diameter, it could be 3 inches in diameter, depends on what you're going to make out of it. This is a situation where they make a forging that has this kind of double keyhole shape or something. They machine the chips out of it. 250 pounds becomes 15 pounds. Here's another one where they do what's called isothermal forging. And 126 pounds becomes 15 pounds. What's isothermal forging? Well, isothermal forging is something that was really developed by Pratt & Whitney based on something that was developed in 1938 in Germany, but was lost because of World War II. It was published in 1938, but because of World War II, no one ever paid any attention to it. And it's called superplasticity. Okay? Superplasticity was rediscovered in the early 60s by a faculty member in this department named Al Backoffen. And Don Avery was his graduate student. And Avery and Backoffen actually were trying to make finer and finer grain size metals. Backoffen's specialty was what he called deformation processing. This is his book, 1972. I studied with him. Actually, he was the first guy I ever worked with. As a sophomore, I had worked in Virginia Beach. Well, after graduating high school, I got a job with the post office. I had to fill out a form, and I scored better than 92%, and so they hired me. Best job, one of the best jobs, if not the best job I ever had. $3.05 an hour. Typical wage for a student back then was $1 an hour. I was getting paid $3.05, you know, whatever a postman makes today. I was getting paid a postman's wages. And I spent that whole summer driving around Virginia Beach in a station wagon delivering special deliveries. Actually, it was only the second half of the summer. When they found that I was trustworthy and I wouldn't just stop for a coffee and stay there for 4 hours, that I actually would deliver the special delivery letters. Back then, a special delivery letter was an extra 35 cents in postage. So they paid me $24 a day to deliver 12 letters in Virginia Beach that had a $3.60. If you want to know why the post office was losing money, I can explain it to you someday. Okay, but in any case, they found that I was responsible. They liked me. I went off to MIT. The next summer, I reapplied, but because of the Vietnam War, you know, I scored 98 again on this civil service exam. But I wasn't a veteran of the Vietnam War, which gave you a 10-point preference, and I couldn't beat the 108s. Okay, you know, I would have had to score 108 to beat some of the veterans, which was fair. So I got a job at the Naval Air Rework Facility in Norfolk at $1.92 an hour, rebuilding jet engines, mostly coming back from Vietnam. And then but I needed to make that same amount of money to afford to come back to MIT, so I took another job at $1 an hour at the job I'd had 2 years before at a drugstore in Virginia Beach. So I was working 30 miles apart, 2 40-hour-a-week jobs. That was not a great summer. The previous summer was great, cruising around Virginia Beach in the station wagon. Didn't have air conditioning, but still, it was okay. Those of you who know Virginia Beach, it was at the time the 5th largest city in the world in area. Okay, half of them, as my father used to say, about Chesapeake, Virginia was 3rd largest city in area. My father used to say it had more bears than people in Chesapeake. But anyway, but in any case, it was a great job. But I decided when I came back for my sophomore year that I did not want to go through another summer like that. So I got a job with Al Backoffen. He was my first instructor in materials. When I started to major in the department. And so I started working in his lab. Anyway, Backoffen was one of the crustiest faculty members ever to be at MIT. Okay, he used to throw books at his graduate students. Okay, literally. Okay, there's a lot of great Al Backoffen stories. But the man was also a genius, okay, in terms of deformation processing. And he was looking at titanium alloys, zircaloy, which is nuclear reactor material, and he was looking at if he made the grain sizes finer and finer and finer. And the reason he was looking at titanium and zirconium alloys is because he could cycle them between these phase transformations so he could get extremely fine grain size, down to 1 or 2 microns in size. This would be called nanotechnology today, okay? It's not nano, it's micro, but anyway. But someone would call it nano today. And he found that he was measuring this M value, okay? M is the strain rate sensitivity. Dion Lee, Korean, worked with Backoffen maybe early on. But if you look, without going through all this, he could get elongations not of 20 or 30%. If he got to very, very fine grains, he could get 1,000% elongation. If he got the M value, turns out M is a very strong function of grain size. If you get super fine grains, you can get extremely high abilities to stretch a material. So this actually it's 1934, the Germans. This is a picture from the German paper of a tensile bar of superplastic material. Bismuth tin eutectic alloy. And there it is, you know. A lot of stretch, okay? So now you got something that acts like glass. You're not at 1, but even glass is only about 0.9. And you can get 0.7 as an M value in metals. It can go from 0.2 up to 0.7 if you get super fine grain size. This belongs in the Smithsonian. It's been used as an ashtray before I got it. I told you about the 8137. That was Backoffen's graduate students, the little short door. That was my first office. So Backoffen's last graduate student was graduating the week that I came as an assistant professor, and I recovered a lot of his old samples. So here's a forging sample that we probably won't go through. Here's a rolling sample. These are Al Backoffen's old samples that he left because MIT was treating him like dirt. Of course, he treated them like dirt, so I'm sort of fair in return. He had a home up in Marblehead, and he decided that he would put it on the market for an outrageous price, $90,000. And if anyone bought it, he and his wife, they had no children, were just moved to their farm in New Hampshire where he was growing Christmas trees. Well, it turns out the first person came by offered him asking price. I mean, he didn't quite figure out what the market really was, so he sold his house for $90,000 or $95,000. He moved to New Hampshire, and every 3 or 4 months he would come back down. He'd stop in and see me because I had been his undergraduate student in his lab, and he was always nice to undergraduates and master's students. It was his doctoral students he would throw books at and curse them and throw them out of his office. Anyway, but he got great results out of his doctoral students because he put them through so much pain, okay? And he never wanted to see a thesis that was more than 30 pages in length, a doctoral thesis. It would take them a year or 2 to condense their thoughts down to a nugget, okay? And his book is nothing but nuggets of the theses, okay? I mean, I read theses that are 400 pages long, and they're telling me that Boeing makes airplanes. You know, thank you. I read for 10 pages about Boeing makes airplanes, okay? But Backoffen's theses were so condensed, and his text is so condensed. But in any case, this is an aluminum zinc alloy. And what Backoffen did is he went down here to Taunton, Massachusetts. He got some dies from the silversmiths. This was a candy dish die for making silver, you know, dishes from the guys down here. Ordinarily, to make a draw like that would take 4 or 5 drawing operations in the sheet metal. With the superplastic material that has 500% elongation, you can do it in a single draw. Okay? That is the reinvention of superplasticity after the Germans in 1934. Okay? That's why it belongs in the Smithsonian. But it makes a nice ashtray, except I don't smoke. Okay, this is what you would do otherwise. If you wanted to make, if you had a piece of sheet metal, you take a blank, and I don't have just the simple round blank, and you would first draw it into something like this, then you would redraw it into something like this, then you draw it again into something like this, and you finally end up with something like this. This is also Backoffen's. I guess I could get another one. This is not all that different than the way you make beer cans or soda cans, okay? Lots of different drawing operations. The dies to make a beer can run for about $2 million even today. Big machine, very complex, but a lot of work's been done on it. So you have to go through lots of steps, okay? Because most metals have a lousy M value and they'll rip with more than 30% strain. So you have to go through operations that don't have more than 30% strain. You can repeat the operation, but if you want to get to something that has 200% strain to make it, you got to do a number of different, 0.2 to the 6th power or something, right? To get all the strain. Yep.
So this is happening with the metal at room temperature?
This is all room temperature. Superplasticity in some alloys you can get at room temperature. That aluminum zinc alloy, that occurs at room temperature. In the nickel-based superalloys that they make turbine discs out of today, when you have isothermal forging, wherever I had that, I showed you a part of a oh, it's under here. Oh, it's not under there. Yeah, it is under here. I showed you this thing where you would ordinarily have to start with a 250 pounds of a $100 an hour, $100 a pound alloy, and to make a 15-pound part, you would generate 235 pounds of chips in machining, which is pretty pricey. You start out with 160 pounds, 126 pounds. It's a single set of dies. The dies are heated to the processing temperature, which might be 1,000 degrees centigrade. So you're using some very expensive dies, but you only have to make one set of dies, and you don't slam it down like a hammer forging. You come in and you squeeze it slowly, okay? But it's reasonably slow. You probably do this in 10, 15 minutes, but in a single set of dies, single forging operation, and get near net shape. A lot fewer chips. Look at how much money you're saving on machining of these things. Yep.
So for these other stamping operations,
Yep.
what causes the system to relax so you can stamp it again?
It's actually the frictional boundary conditions. You got lubrication on the surface, and as you stretch it out, you get non-uniform straining. Should have pictures of that. Actually, why don't we do it this way? This is in my opinion, the most important graph in Backhofen's book. Okay? It's called deformation zone geometry. And frankly, a lot of the way I look at the world is based on Al Backhofen's approach of how can you generalize everything into just a couple of simple principles. And here he has the pressure to do the forming divided by 2 times the shear stress. I mean, if you're going to change the shape of something, you're really shearing the metal. 2 times the shear stress is really the tensile stress, the flow stress of the material. So at 1 to 1, this is basically just a simple compression test if P over 2 tau y is 1. And this is just a simple compression test. This is called, the title of this chapter was chapter 7 in his book, is called Deformation Zone Geometry. Okay? And it doesn't matter whether you're talking about Play-Doh or lead at room temperature or nickel-based superalloy at 1,000 degrees, this deformation zone geometry always applies. Okay? For virtually any homogeneous material. And what it says is if you have a deformation zone geometry where delta, which is the height of the deformation zone divided by the length of it, is less than 1, well this is 1, this is less than 1 for delta. The height is, this is a thin sheet versus a length of where the tooling hits it. Anything less than 1, you're just doing a simple compression test, and that's the load that it takes to deform that, whatever the shear stress of the material is. As you get to something like a hardness test, where you're running a punch into something that's very thick, if this is a non-work hardening material, without going through the other chapters in Backhoffing ahead of this, it's 1 plus pi over 2, or 2.57, okay, times as much force. If any of you have ever done any hardness testing, you may know that there's a rule of thumb that the hardness of a material is 3 times the tensile strength of the material. There it is, 2.57. And then add a little bit for work hardening, you get to 3. So as a rule of thumb, a hardness test takes 3 times the pressure force of a simple compression with a deformation zone geometry of 1. You essentially are infinitely thick if you get up to 9 or 10 as a deformation zone geometry. Okay? Now, the deformation on thinner things is inhomogeneous. This is on kind of the next page of Backoffen, or 3 pages later or something. I don't know how well that shows up, but here someone just took a punch with a 5 millimeter face and just squeezed onto a plate that was 30 millimeters thick, and they did it in a particular type of steel that has some nitrogen in it, that when you etch it the proper way, here they did a little bit of deformation, a little more and a little more. You can actually see the deformation geometry, the localized plastic flow in the material, and it's exactly what you get from this type of an analysis at that was the one I just showed you with 5 and 30 is actually a deformation zone geometry of 6. But this is one where he's drawn it here at 4, okay, of delta over H. This is inhomogeneous straining of the material. And if you keep going on Backoffen, let's see. Oh, here we go. Here's a couple of Backoffen inhomogeneous strains. This is actually good old plasticine clay models from 1931. This is typical Backoffen. Nothing's new. It's just explaining the old stuff, okay? Here we're extruding something, plasticine, and they basically put some grid lines on there. So originally it was a nice square grid. Here we have a nice tapered angle. Here we have a sharp angle, just changing, making a sharper and sharper angle. If you're squeezing toothpaste out of a toothpaste tube and you have a nice gentle angle, the strain lines, they're no longer straight across. They're approximately, well, they're not very they're a lot less inhomogeneous than here. Look how that line changed. It's the same amount of reduction, area, diameter reduction, but you have a tremendous difference in the amount you're straining the material. Yep.
But one on the far right is what's happening in all these pressing operations.
Well, far right, this side, yeah, okay, yeah.
So you have some piece of cold metal in a press that you're going to form.
In a forging press, yes. Yeah, it can be something like this, but it really depends on the angle. It's not all of these. Okay.
So if you deform it,
Yep.
why can you then go and do that again as opposed to just doing all of those?
Because you relax everything, you don't have the same friction. The reason I'm getting this inhomogeneous deformation is because the friction of the tool is pulling on this material. Here, the tool friction is not anywhere near as important. Okay? In fact, chapter 8 is frictional boundary conditions in Backoffen's book. So if you start with you started out with a lubricant on the surface. If you don't have enough lubricant, you actually start cold welding the material to the surface. Okay? If you take it out and re-lubricate it, you can go further again. Okay? So it has to do with the friction on the surface. If you start welding it together and start sticking, and you get more than 30% local strain, it breaks. Okay? But if you deform it, don't break it, take it out, put it in another tool that's lubricated again, re-lubricate the surface, then you can start deforming again. Okay? It's not the absolute strain, it's the local strain that causes the fracture. Okay? So it's the lubricant on the surface and re-lubricating. And the reason you can make that little part, I said they used iron phosphate to put a thin layer of lubricant on those things. Yeah, if you get a thick layer of peanut butter in there, your lubricant takes you further, okay, and lasts longer. They don't re-lubricate between each one of those. They still have to do a step to kind of get started again so that they don't get some thin spots, but they have enough there that when they put it in a new die that they get the thing re-lubricated properly. Okay, so it is the frictional boundary conditions which we can go through. Well, actually we're not going to go through. This is another Backhoffen thing from one of his students' doctoral theses, where he looked at wire drawing. He just looked at the hardness of the material, and this is new hardness number. This is lubricated strip. This is unlubricated strip. Okay, to emphasize how lubrication makes the difference. So here's the same angle, but the inhomogeneity factor, which is what he called this, the ratio of the highest hardness to the lowest hardness, drops from about 128 to 123, depending on the lubrication. Okay, and if you have a sharper angle, a very shallow angle, you can get very homogeneous straining. Depending on your angle and your lubrication, if you get too much strain at the surface, that's where the cracks start. Okay, at the surface. And so if you initiate a crack, you're done. Okay, you probably try to put in another die, it's already got a crack there, then fracture mechanics tells you it's just not going to work. Okay, does that answer it? You're still looking puzzled at me. But pardon me? Oh, he looks puzzled? Okay, well, there are other things that cause inhomogeneity. This is out of Backhoffen. This is actually drawing, this is from the same student's thesis, okay, master's thesis in 1965, where he was drawing with this inhomogeneity factor. You actually can set up tensile stresses in the center and cause these things to crack. And that's a type of defect in wire drawing or extrusion that you can get. Backhoffen used, of course, his student's thesis. He didn't use this, which is an even better drawing. This comes from Don Blickweed. Actually, I guess he did. No, one of Backhoffen's students used Blickweed's. Blickweed was a student of Morris Cohen. And Don Blickweed was the vice president of research when I went to work for Bethlehem Steel. This is work that Don Blickweed did when he was at Bethlehem Steel. But he was a Morris Cohen student, so Backhoffen would never put a Morris Cohen student's pictures in his book, because he didn't get along. These are the internal politics of the MIT department. But anyway, this is extrusions of Blickweed did, showing the type of defects you can get if you don't have the right lubricant, the right contact angle, the right percentage reduction. Okay, so just something as simple and has been going on for 4,000 years is drawing wires through a die. You got to know what you're doing, and you got to get the right set of parameters. Okay, or you can just turn out junk. So there's a whole science to this stuff. There's a science to rolling of metals, and we're not going to go through all this stuff, but it turns out one of the things when you're rolling sheet metals or plates, you want to have nice big plates, nice wide plates, so that people don't have to make as many welds between plates and stuff if you're building something big like a ship or a bridge or something. The problem is you can't make the rolls too big. If you make the rolls too big, when the roll flattens, when you're putting stress as you're compressing, as the roll is compressing on the part, you're putting stress, compressive stress on it, which causes the roll to actually slightly deform. And there is a rule of thumb, which I've never seen anywhere except in Backhoffen's book, except I've experienced it a few times, that at a ratio of sheet thickness to roll diameter of about 500, you can no longer get any deformation. You can roll through that thing and have the gap completely zero. The rolls in contact with each other. When you put the elastic material in there and you get the elastic spring back of the rolls at a ratio of diameter to sheet of 500 to 1, you can have zero gap and the thing will just go through there without deforming the sheet at all. Well, what that means is you got to have smaller diameter rolls to roll thinner material, which they do, but then If the roll gets too long, it just becomes a flexible beam. So they have backup rolls, and they call this a 4-high mill, because you've got the work rolls and you got the backup rolls, which are larger diameter and stiffer. These have to be small diameter. Here they have something called a planetary mill, and they actually put little rolls on here, and you get something that's all a surface that's all wrinkled, and you have to put it through a final roll. But the more interesting thing is a Z mill. This is a Zenzermer mill, where if you want to make foil material, it's 1/1000th of an inch thick, they can roll material to 1/10 of a thousandth, but they can only do it about a couple of feet wide, a foot or a couple of feet wide, because the Z mill rolls, the work rolls, can't be more than 500 times the diameter of the thick sheet, right? If I'm talking about 1 mil sheet, that can't be more than 1/2 inch in diameter. If it's 12 inches long, you can realize it would, that would just break, it'd just bow, okay, in fatigue. So a Z mill, they call it Z, but it's Zenzermer, which is this Hungarian metallurgist. He has a set of backup rolls, and he has 3 backup rolls, and then he has 4 backup rolls, and it goes through something like this and to roll that foil down. Foil can get to be very expensive, except what's the most widely used foil in the world? Reynolds wrap. Why is it called Reynolds wrap? Anybody know?
Guy named Reynolds.
Yeah, but he also had a bigger company. He started an aluminum company called Reynolds Aluminum because he needed aluminum foil to package his cigarettes. They're all in Richmond, Virginia, folks. Okay? Reynolds Aluminum was started by the guy who was making the cigarettes and wanted to have something that wouldn't lose or pick up moisture, so he needed a hermetic type of seal. Not completely hermetic, but he wanted to keep the cigarettes just the right moisture, right? But aluminum foil is done by what they call pack rolling. They just put a bunch of sheets of aluminum through and they roll them through. The problem, and so you may be rolling 100 sheets of aluminum in one pass in a special mill. I've been near an Alcoa foil roll, but they wouldn't let me get any closer. There's a little bit of technology here that they don't want everybody to know about. But it is called pack rolling, and you just lay up a bunch of sheets. So it's like taking a ream of paper and putting it through the rolls, okay? The problem is you now have to segregate it because you have different amounts of deformation on the edges versus the center because the inhomogeneity, the frictional boundary conditions. So the thinnest aluminum foil comes from the top surface or the bottom surface, and the thicker aluminum foil comes from the middle. Yeah.
Is there lubrication, or how do you keep it from?
Oh, aluminum is nice because it has its own nice aluminum oxide, and they probably do have some lubricant on there, but I have not seen it, and you won't find a lot in the literature because it's sort of well, first of all, there's only so many companies that do it, okay? And they don't like to tell everybody how they're doing it, okay, because it wouldn't be hard to duplicate, okay? The world's largest rolling mill is located in Davenport, Iowa. It belongs to Alcoa, and they roll the plate for the wings of 747s and things like that, okay? It's not particularly high tech, okay? I've been there. I had a student do a thesis on it, on trying to control the gauge of the plate and the way they measure the gauge of the plate in the aluminum mill. The world's largest rolling mill. This is like 8-foot diameter rolls and about 15 feet long. They have a guy, he's got a little step ladder, 2 or 3 step wooden ladder, and they stop the mill. He pulls the step ladder up, he pulls out a micrometer, he goes up there and he measures it. I saw that, I thought, wow! As an old steel guy, hey, you'd never do that at a steel mill. But the volume of aluminum is not as great, and so they didn't do that. Now what a student's thesis was about, this is about 20 years ago, is they were finding that the plate was coming in off gauge, and they had a significant fraction, I don't remember the numbers, but like 20% of the plate they would roll would not be the proper thickness. Well, they're only measuring at one location. In a steel mill, they actually would have a radioactive source, and they're measuring the intensity of the x-rays coming through to determine what the thickness is. So they're measuring online along the whole length of the strip that they're rolling, but not in an aluminum mill. And thick plate's a little bit harder to do that anyway. With the radiation, you have to clear everybody out of the mill. So they only measured at one location, but if you looked along the length of one of these plates, they were getting things that looked like this. So that's what the student did. She went out and she had a thickness gauge after they finished rolling. She actually mapped them. Some of them had it on both ends. Some of them only had it on one end. Okay? And it depends. If you measured it here, you got one thickness. If you measured it here, you might be on a 3/4 inch plate, you might be 20 thousandths thicker. And that's why, depending on when where they measured it, they were getting different values. Well, so she went out and she measured it. She came to my office. This was a LFM thesis. She came back, showed me the data. We were sitting in my office, and I'd visited the plant, and all of a sudden it's one of these. Oh, I know what it is. It turns out this is hot plate that the guy's rolling. Now, hot is only 700-800 degrees Fahrenheit. Okay, but to keep the rolls cool, they actually kind of flood them with water. So as it's going through, this hot aluminum plate is going through. It kind of is going through a little waterfall of water. It's not a heavy waterfall, but it's raining on the plate. It turns out they intentionally run the top roll just a little faster than the bottom roll, because you don't want the stuff, if you're rolling and it's coming out this direction, you don't want it to curve and go into the bed, which is a bunch of rollers that are holding the plate. If it does that, you'll get what they call a cobble. It goes in, it jams into your roller bed, and you just start tearing up everything, because you got this massive, I don't remember how many thousands of horsepower you got on these rolls, but what's pushing on it is pretty strong, and you'll just destroy everything. So they want it to slightly curl up, right? Well, so they roll the bottom one a little faster than the upper one. Okay, anyway, so there's just slightly out of sync on speed, so that you get a slight curve up. Well, it turns out you got water coming down here, and I remembered when I was there, sometimes I would see water pooling on this little cusp. Sometimes it would come through and it's nice and flat and the water would just roll off. But sometimes there was enough of a curl there, the water would collect right there on the end. What happens when it collects there on the end? 700 degree aluminum, boiling water, right here, thin film of boiling water, cools this down, okay, right on the end, which is where it would collect. And now this is cooler than this, the main body of the plate. And so when it rolls it doesn't roll it as much, and you would get something that's a little thicker on one end or the other, depending on whether you pooled your water. And I said, well, so I had her go through and do some estimates. We could explain 80% of the variation they were seeing by my estimate, or our estimates of the cooling that you got, and how much increase in strength of the colder aluminum on the ends of the plates, depending on whether the water was on there. Well, what's the solution? You blow the water off with compressed air. They got plenty of compressed air at the plant. I figured it would cost about $10,000 to put an air knife on there, which is just, blow the water off. So did they do it? No. They would have recovered the $10,000 on a single aircraft plate that they didn't have to scrap for being out of spec. So anyway, she turns in her thesis. I happen to know the guy, Owen Richmond at the time, who was head of deformation at Alcoa Labs. I said, hey Owen, we figured out what the problem is out there at Davenport. And I explained it to him. I said, all you need is an air knife. I figure it won't cost more than about $10,000 to fix it. He says, oh, we'll get that done, Tom. I said, no, you won't. He looked at me and said, no, you guys, you're a big bureaucracy. You won't be able to do that. Okay, he said, there's no one there who would have the authority. I don't remember how snotty I was, but anyway. But I basically told them, no, they weren't going to fix it. This was Alcoa, okay? They were not, I knew Alcoa's, their whole philosophy was, Alcoa at that time, this is 1990, was a big time not invented here, okay? If it wasn't invented at Alcoa, it was garbage. There was no value to it. So this wasn't Alcoa's idea, they weren't gonna do anything. So I said, he says, yes, we will. I said, Owen, I'll bet you $10,000 you won't. Okay? So a year later, we're sitting on the committee together again. I said, hey, Owen, you ever put those air knives in Davenport? He just turned around and walked away from me. I'll bet you they're still not there. So there's a little lesson there. Okay, I'll talk to you later.